Hello, this is Mathematically Speaking. I am your host, Adam Allred, and welcome back to the show. Egypt is our next big stop on our mathematical journey, and its timeline overlaps quite a bit with that of Mesopotamia, so it's not that unbelievable to think that they knew much of what Mesopotamia knew. However, there is some knowledge that is unique to Egypt, which is what we will be discussing over the next two episodes. Egypt's history begins in the year 3100 BC with the unification of Upper and Lower Egypt. Around 2700 BC, we get the first instances of hieroglyphic writing. Within the next 100 years, the Great Pyramid of Cheops was built. Egypt is eventually conquered by Rome in the year 30 BC, with Cleopatra as the last queen of Egypt. And interestingly enough, most of the accounts that we have of her are Roman accounts, who saw her as a threat to the Roman Republic, where they claimed that she was famous for nothing but her looks. Even though she was extremely intelligent, a talented strategist, she spoke 10 to 12 languages, was a published author in everything from medicine to measures. She's intimidating for sure, but not just because she's pretty, because she's a badass. She was a classic ruler for her time, except for the fact that she was a woman. And under her, Egypt flourished. And as we know, Egypt was built around the Nile River, which had a regular flooding schedule, similar to the Mesopotamian culture, which was developed around the Tigris and the Euphrates rivers. This regular flooding gave rise to an easy concept of a year and the idea of a logical universe. This could be part of the reason why mathematics and then philosophy began here when it did. If you believe that you live in a logical universe, then it must be possible to know things about and to reason about that universe. There must be reasons for everything happening around you, and mathematics is one of the ways to know those reasons. There's also an interpretation of mythology that myths perform this same job. It will be some time before we're talking about China, but this pattern didn't develop there. The Yellow River did not have a cyclical flooding schedule, which potentially impacted the philosophy of China. So where no formal logic flourished there as it did in Africa and the Middle East, rather they started with ethics, but more on that in a few seasons. The writing tech of Egypt was closer to ours than that of Mesopotamia. Clearly, we don't have clay tablets. Egypt had papyrus, which is essentially very thick paper. And it was made of the pith of the papyrus plant, which is considerably more versatile than clay tablets. It was lighter, so it could be made to any size that the writing wished. This could have impacted the notation that was chosen for their numbers, and most of our knowledge of what they knew came from the Rhind papyrus from 1650 BC, the Moscow papyrus 2000 to 1800 BC, and the Berlin papyrus from about 1300 BC. The Rhind papyrus consists of problems and their solutions similar to a modern-day textbook, and their problems spanned arithmetic, geometry, unit fractions, composite and prime numbers, geometric and harmonic means, solving first-order linear equations, arithmetic and geometric series, and these subjects span the beginning of mathematics to the beginning of calculus. The Berlin papyrus gave us evidence that they knew also how to solve quadratic equations, which we covered in the last episode. Now, when we're covering Egypt, we're not going to be going over all of those things that they knew. We're not going to talk about prime numbers or harmonic means or first-order linear equations or geometric series because, one, we don't know how much they knew of that. We just knew that they knew it. We don't know how much theory they knew, and that mathematics in the West wasn't developed until well after the Renaissance. And I'm going to save it for when we get there. Now, the Egyptians had a base 10 grouping notation, meaning that each marking denoted a group of 10. The vertical line was a 1, an arch or inverted U was a 10, a 100 was it was supposed to signify a coiled rope that had some string coming down, and a lotus flower was supposed to be 1,000, and they had markings up to 10 million. And this kind of notation made positioning irrelevant. It didn't matter the order of what you put your symbols in, because each symbol had a specific meaning. It's kind of like money. If you give me a bunch of money, and let's say bills, and there's ones and fives and 20s and 50s, and I jumble them all up in a different order, it doesn't matter what order they're in, because they still represent a 1, a 5, a 10, a 20, or 50. And this kind of notation made addition and subtraction very easy. You would gather them up, sort of like how we're dealing with money. So they had coins with sort of like how our coin money is. There's, in the US, it's sort of weird. Everything's by size. You just know how much it's worth by its size. In other places, it's how much it's worth is on the actual coin. So they would have a coin with a vertical line on it for a 1, a coin with an arch on it for the 10, a coin with a lotus flower for 1,000, etc. And you just group up, knowing how many inverted U's it takes to make, how many arches it takes to make a coiled rope. How many 10s does it take to make 100? 10 of them. So I would take my 10 arches, all those coins, and then I could transfer them for 1 coiled rope, because 10 10s make 100. And that kept the information, which is what arithmetic is about, keeping information, allowing you to play with it, and making it smaller and more compact. So addition and subtraction is very easy. You're just exchanging. But how would multiplication and division work? They had to be based on addition or subtraction. The Egyptians had algorithms. One of them was known as the doubling algorithm, which I'm going to do my best to orate an example of. Imagine you're an ancient Egyptian, and you want to multiply 67 and 51. Why you want to do that? Don't ask questions. You just do. So you take the bigger number, 67, and you begin doubling it, which is just adding on multiples of it. So I'm going to add on, to multiply by 2, I'd add 67 and 67. Multiply by that by 2, add 2 more sets of 67. Multiply that by 2, add 2 more sets of 67, etc. And you want to keep track of the multiples of 2. So example 32 is 5 multiples of 2, because 2 to the 5th is 32. You do this until your multiple of 2 would exceed your other number. In this case, we're going to stop at 64, because 64 is bigger than 51. And then you start subtracting away with the highest multiple until you reach 0. Add up those numbers, and we get our answer. Another algorithm, which is much easier to understand, is known as the peasant's algorithm. You take the bigger number, 67, and you begin doubling it. You take the smaller number, 51, and you begin cutting it in half. And you round down if you need to. You look at your you want to keep this organized, of course, so you have this in columns and rows. And every row with an odd number, you add up the column. That sum is your answer. This one is considerably more simple, and if I had to pick one of these two, I would do the peasant's algorithm. But it's because they only rely on addition as the method, making them relatively simple to perform. The next and last mathematical achievement for this episode involves dividing bread. What if we want to split 2 loaves of bread among 9 people? We want to make sure that everyone has an equal amount. How do we ensure that everyone gets their equal piece? Or another way to think of this mathematically is, how can we write the fraction 2 over 9, because we're dividing 9 into 2, 9 people need to get 2 loaves of bread, as a bunch of unit fractions, where everyone just gets a piece of bread that is a fraction of something else. Well, you could just say, well, Adam, you just add 1/9 plus 1/9. But their notation didn't allow for writing fractions with the numbers greater than 2 on top. So for unit fractions, it would just be a 9 with a bar on top. So 9 bar is how I'm going to say that. So 2/9 would be 9 bar plus 9 bar. Now, our notation may seem more obvious, but our notation was developed over hundreds of years of math and notation change. So if we focus more on the division concept of fractions instead of fractions, like splitting loaves of bread fairly amongst everyone, then these fractions become a bit more interesting. So just to have a more interesting example, what if we have 4 loaves and 5 people? That's almost enough for a full loaf per person, but unfortunately, we don't have that. We must know how much each person gets before we begin slicing the loaves of bread so that we don't have too many cuts. So first we're going to divide 5 by 4 and then round up. That becomes the bottom of our new fraction, which we will subtract from 4 over 5. This is going to be repeated twice. So we're going to get 4 over 5 is 1/2 plus a fifth plus a tenth. So how do we slice each loaf? You're going to slice 3 of them into halves and give one of those halves to each person. The whole loaf that is left, you have a leftover loaf, you're going to slice that into fifths and give each fifth to one of those people. The remaining half a loaf that we have is sliced into fifths, which are now tenths, and each person gets one of those. This has fewer cuts than just cutting every loaf into fifths and each person getting 4 of those fifths. And it makes it appear that each person gets the equal amount and nobody has a bunch of the ends of a loaf because nobody likes the butt of bread. They didn't then, they don't now. This has been Mathematically Speaking. Tune in next time where we talk about the Great Pyramids and discuss whether or not this universe was created with a single number. Thank you for listening.